And we are live. Welcome back, geometry students, to volume and density day 2. So, building off of what we learned yesterday, we have 5 different shapes that we'll be able to find volume and density from. And then thinking back to earlier in the week and even yesterday, we have to find some areas. So all of this is on your reference sheet for the state test. But let's go ahead and jump right in to these problems. So working in groups of 2 or 3, go ahead and put your brains together and try to work through these, and then watch the video to get the answers. Okay, we're given a regular hexagon here, and we want to find the perimeter and the area. So if we remember, for a regular hexagon, we make shapes into triangles here. So when I do that, I need to draw my apothem and make that into a triangle. Now, thinking about a regular hexagon, to find that central angle, you do 360 divided by 6, because there's 6 sides. That equals 60 degrees. Now, that is the whole thing here. When this gets cut, just one side of this is 30 degrees. Okay, so then you have a 30, 60, 90 right triangle, which I'm drawing off to the side here. So in our case, that's 30, it's the 60, and we know that one side is 12. So we can go ahead and apply our knowledge of 30, 60, 90s to say that this side is 6 radical 3, and then the other side is just 6. So special right triangles, get to know them, get to love them, get to use them. They can solve all the world problems. Okay, now to find the area, since we have now found our apothem, is 1/2 times 6 times 6 radical 3, and then we made 12 of those little triangles, so we'd have 12 dots all around here if we cut all of these into special right triangles, so that's why we multiply by 12. And the area equals 374.12. Now the perimeter, pretty simple, because if I go back to our special right triangle, the apothem was 6 radical 3, and then just one side is 6, and I have 12 of those little dots that are all representative of 6. So my perimeter, just counting all of those up, would be 72. Okay, the globe and cube problem. We did one like this yesterday. I'll go ahead and still draw another picture for you. So we have this cube here, and then we have a globe or some type of ball-shaped object, and we want to take this and put it inside of the cube. So pretend this is opening, we put it right inside of the cube, it sits inside of there, and we want to find all of the open area where there's corners open or sides open, anything like that. So the area or the volume of the space that is not taken up by the globe. And we're told that the diameter is 16, the cube has, let me change colors. Cube is 16, 16, 16. Remember, it's just made of squares, and we're told that the diameter of the sphere is also 16. So for the cube, the area equals base times height, or area of the base times the height. So the area of the base would be 16 by 16, and the height is also 16. So area in this case equals 4,096. For the sphere area, if you look at your reference sheet, is 4/3 pi r cubed. Now, if our diameter was 16, then half of that would give us our radius, which is 8. And then we cube that. Plug that all into your calculator. 2,144.66. So now we want to take our two answers and subtract them. We want to know space left over. And that's just 4,096 minus 2,144.66. So the space left over, 1,951.34. Remember, this was in inches, and then for volume, we do inches cubed. All right, moving right along to our next problem. A cone and a sphere have the same volume. The height of the cone is 96 units. So then what could the value of the radius of the cone, or what could be the value of the radius and the cone and the sphere? Round your answer to the nearest hundredth. So let's just go ahead and draw a picture real quick. Pictures help a lot. Here's your cone, and this has a height of 96, and then we have some type of sphere, and this sphere, these areas are equal. And they want to know, well, what could the value of the radius be? So your radius in purple would be here, and your radius in purple would be here. Now these pictures are not drawn to scale. Those two radii have to be the same. So to solve this, if they have the same area, let's set their formulas equal to each other. So for a cone, 1/3 pi r squared h. For a sphere, we just did it above, 4/3 pi r cubed. And we want to get this in terms of r. Now we do know, however, that the height of the cone is 96 units. So I can go ahead and plug in a 96 there. So just by quickly looking at this, we can eliminate some stuff here. If I divide by pi on both sides, well, those pi's are simply just going to cancel out. Now, if I divide on the left by r squared, these will cancel, and r cubed divided by r squared just leaves me with r. Remember, when you divide exponents, you subtract those exponent values. So 3 minus 2 would be just r to the 1. And then 1/3 of 96. I could go ahead and simplify that down to 32. So 32 equals 4/3 r. And our final step here To undo that 4/3, we have to multiply by the reciprocal of 3/4, and 24 equals r. And remember, these radii have to be the same. So you just had to set this up geometrically, but then it turned into one big algebra problem, and you all are rock stars at algebra. Number 4. A company wants to design a cylindrical object that has a height of 10 centimeters and a volume of at least 2,000 centimeters, but no more than 2,500 cubic centimeters. So what is a possible radius of the cylinder? Okay, so I'm going to draw a picture here. Here's my cylinder shape here. Okay, something like that. We're told that height is 10, but we want to find the radius. We want to know what is a possible value of r so that we can satisfy both of these. So the min volume that we can have is equal to 2,000. So let's set up the problem and solve it for 2,000. So 2,000 equals, our cylinder formula is pi r squared times height, or in our case, 10. So we want to solve this for r, so I'm going to divide by a 10 pi to get 63.66 equals r squared. You undo a square by square rooting, so 7.98 equals r. So this is for your minimum value. So now if we can say, well, we have a max value of 2,500, just thinking logically about this, our radius should be slightly bigger here. So 2,500 equals pi r squared times our height, which was 10. Same process that we just did, we're going to divide by a 10 pi to get 79.58 equals r squared. And then you undo the square by square rooting. So 8.92 equals r. So again, it is slightly bigger. And these are both of the possible radii that you could have based on your parameters.